Video for my package called UFS. It stands for Unsupervised Feature Selector. It's a package that's supposed to help with determining which factors or which variables are really important to start collecting at the beginning of a data science project. It was inspired by a project I worked on last summer where we were trying to find early warning signs for opioid abuse. And the big problem we had when we were developing this project was that we had a big sample of people we could query for information, but we couldn't get any output variables, like if they actually suffered from opioid abuse until several years down the line. So we had tons of opportunity for input data, but we didn't have any outputs. And so what we wanted to do was we wanted to decide which questions were most important to ask people during checkout visits, during their initial visits, to determine in the future if they're going to suffer from opioid abuse. And there's a lot of literature out there talking about how to do this if you have the output variable in hand, but there's basically nothing that talks about how you do it if you know nothing about the output space. And so this is kind of what this package is trying to help accomplish. So we do this through a method called GVM, Greedy Variance Maximization. It's a lot like PCA, except it actually reduces the dimensionality of the input space rather than just reducing the dimensionality of the transformed input space. So what does that mean? Basically, PCA, what it does is if I have 300 variables I'm collecting, it takes a linear combination of those 300 variables and outputs 2, 3, 4 of the most important combinations. But that's a problem because you still have to collect all 300 variables. With this solution, it just takes the 5 most important input vectors and discards everything else. So this is great for the problem we were trying to solve, because now we don't have to ask everyone in the practice 300 questions. We can now ask them 5 questions and get effectively the same information. So kind of going through this package to show what it does, the library is called UFS, and included in the library is a default data package called Senate. This is the Senate records for the last congressional year. I think it was like 2015 or 2016, and it includes 374 columns that are all the bills that were voted on in that year, and 98 senators that make up the rows. 2 senators have been discarded because they were voted out of office halfway through. It also includes information on the party of those senators and the party data frame. And as I mentioned, it's a 98 by 374 and a 98 by 1 matrix. So the backbone of this entire program is built on GVM, which is built on another program that does another function that does all the output work for us, called plot reduced. And so plot reduced is a really cool function where basically we take in the data frame and it will automatically run PCA on the row or the columns of that data frame. So reduce it from 300 or 900 or whatever we have down to 2, and then it will plot those reduced vectors. So running it on the Senate data frame gives an output plot that looks like this. And so this is basically a plot of the 98 senators in 2 dimensions. So all the votes they did on all the bills in 2 dimensions. And so it's kind of cool because this function has some extra functionality as well, where I can include a mag, which stands for magnitude, for whatever I want to be a vector of those 98. So for example, if we choose the political party, what it will do is it will automatically color everyone in the party, with the Republicans being colored red and the Democrats being colored blue. And this allows for lots of really cool, powerful graphics, because we can do gradients. So for example, if we're interested in looking at the bills according to who voted for them, it's an easy thing to do. So in this example, these are the 374 bills that were voted on in this congressional proceeding. On the right, we have the Democrats, and on the left, we have the Republicans, or the Republican-favored bills and the Democrat-favored bills. And then towards the middle, we have kind of the more neutral bills that everyone was agreement on. You can also visualize the second principal component the same way. This is the popularity component. So green is more popular, red is less popular. As you move from top down, bills become more popular and more common because people like proposing popular bills. So that's the first function that really handles a bunch of the graphics work for this package. The gradient information is encoded in this convert color function, which is also included with the package for doing custom plots and scatter plots. And all it does is it takes in some sort of arbitrary vector, chooses the color gradient you give it, and then converts everything into that gradient. So it's really nice for if you're doing dot plots or scatter plots or what have you. it'll do all the coloration for you. So really the heart of this package is the GVM function. And so the way the GVM function works, as I mentioned before, is through variance maximization similar to PCA. So the way it works is that you take the input data frame and first compute the displacement vectors. So if you have a row of all ones, they'll all be converted to the zeros. If you have ones and negative ones, they'll pretty much stay the same. Then what you do is you pick the vector of greatest magnitude. And note that the magnitude in this case is equivalent to the variance of that dimension. And so that's really nice because you're basically picking the vector of greatest variance. And then after you pick that vector, you compute the rejection vectors off of that vector. So what that does is that anything that's not explained by that first vector you picked now goes into the second data frame. And then you iteratively retake the same process. So you take the largest rejection vector and then compute the rejection vectors from that. And what you get is that basically an iterative process where you start selecting the biggest vectors with unexplained variance. And this is plotted using this plot reduced function that we developed before, with the mag function being the unexplained variance in the vector. So what's this look like? This is kind of the idea. So just like before, these are the 300 some odd bills that we were developing, and the color is the amount of unexplained variance. So bright yellow is very strongly explained, and the green is the red is very unexplained. The green represents the vectors that GVM actually chose to represent the set. So the first vector it picked was this vector over here, where it's strongly on that kind of first principal component and explains a lot of the variance initially. The second one is this vector in the middle, where it's kind of an oddball bill that was not very well explained by the first one. And so what's actually going to happen is if we try different values here, it's going to pick the values with the maximum range variance. So I'll pick this one first, I'll pick this one next, I'll pick this one third, this one fourth, and somewhere around here for the fifth one. And so if you run that, you can see it picked these 5 vectors, and the amount of red decreased substantially because it's picking the greatest variance, and then it's computing displacement vectors. So that's really nice. We can also do this on the transpose vector. So this is basically instead of looking at the bills, we're looking at the senators themselves. Similar kind of process. It computes the vectors of greatest magnitude and then computes displacement vectors from that. So that's the core function that really is kind of the heart of this package. It does that factor analysis, the unsupervised feature selection that we're really trying to do. But if you want kind of good results and you want to know exactly how well your function's actually doing, you want to compare it against an established method. So for that, we built our own custom PCA, principal component analysis function, which displays the exact same outputs, but with the principal component vectors instead of the chosen vectors by GVM. And so this is kind of what that looks like. You see the exact same diamond shape as before, just like up here. And the 2 principal component vectors it picked was one down here, one up here. And so this first component is just like this component up here that it picked. And this second one is just its second chosen principal component. And note, it is explaining a lot more of the variance than GVM is. And that's because PCA is a more powerful dimensionality reduction method. Because instead of entirely getting rid of the data we have, like GVM does, PCA is taking a combination. So that's nice. We can do the same thing again with the senators. Gets a very similar kind of result. We're explaining a bunch of the variance. It's doing a much better job here than GVM was doing. There's a lot of unexplained variance up here and down here with GVM, but PCA is actually encapsulating most of it. But how much? How well is PCA doing over GVM? And so that's kind of what our next part of this package is trying to do, is trying to explain how well are we actually doing. So the obvious way to do that is to build a scree plot. And a scree plot is just the amount of variance explained per component. So running the scree plot, we can actually see that GVM is actually doing a really good job at explaining most of the variance early on. So this very first component actually explains the majority of the variance in both cases. And while PCA does outstrip GVM, it doesn't do so by much, which indicates that actually most of the data in this data frame is superfluous. We can get rid of it and we can ask fewer questions, which is great. Same thing with the other side. This is the senator scree plot. Similar kind of event going on here. PCA works really well in the first couple of components, It takes a little while for GVM to catch up, but really after 6 or 7, it's pretty solid. So the next thing is, we now know that GVA is working pretty well, or GVM is working pretty well. What if we do if we want to manually change the data frame? So for example, with GVM, we picked out 5 vectors with the maximum variance that are, roughly orthogonal. But, for whatever reason, we want to substitute one for another. Maybe we don't like the question we asked, or maybe like this sensor is really expensive to pick up. What if we want to change something about what GVA does? And so we can do this with this package. There's a lot of tools that allow you to do this to help out with this process. The first one is the nearest vectors function, where it's basically, it takes in a data frame and a vector, and then it computes all the vectors that are close to it. So basically, if there's a question you don't want to ask for whatever reason in a survey, you can check to see what other vectors or what other questions basically give you the same information. So in this case, this is the bills that we're looking at, and we don't want to look at bill 1, so we want to see what similar bills are to bill 1. And what we see is 26. 1 obviously is perfectly correlated with itself. 245, 6, or 250, 265, and 94 are all very strongly correlated with that very first bill. So they're all pretty much substitutable. If we wanted to use bill 94 instead of bill 1, we could do that. Exact same thing with the other side. Bills 1, 55, 17, 7, and 41 are strongly correlated with that very first bill, which is represented right there. Okay, last thing is the variance explained function. And so after we manually kind of manipulated our data frame to decide what bills we want to pick instead of the bills that GVM recommended, we have to evaluate how well those are actually doing at explaining the variance in the initial data set. So this is kind of the exact same output as these two functions up here, the PCA and the GVM functions, where it kind of gives you this plot and then a variance explained in the console, except it takes in a manual set of vectors. So in this case, we're using the variance explained function with the Senate data frame and looking at vectors 1, 2, and 3 and trying to understand how much variance those 3 explain. And so we plot it, and you see the same kind of diamond structure as before. And then these vectors are vectors 1, 2, and 3, and they explain cumulatively 75% of the variance. So that's kind of the breakdown of this package. There are a bunch of helper functions that you can access if need be, but these are the kind of core supported ones. The core idea, again, is to effectively perform unsupervised feature selection, where we're trying to pick out which variables in the input space are most important for prediction without knowing anything about what we're trying to predict. Thanks for your time, and keep on coding.